You can start. Yes. Yeah, so let's begin. Juvenal Murwanashyaka. So you know this. So this English teacher is some, right? Yeah, English people. Oh yeah. Thank you. It's the right region. Yes. I can read it. For me, it's fun. So if I put this still back problem from my a substitution problem. So today I start to tell you about the particular structure of this, and then prove that the analog of impact problem is undecidable by interpreting arithmetic with condition and equation. So X the formula in the language for arithmetic and condition and application. And gives you a lemma in this sequence of this structure. And this marking mark special sentences to previous sentences. So that the sentence is to here, what part is to here, and then by start is to that structure. And then using that the analog of Hilbert problem is undecidable. Then we can conclude that there is also no analytic from this side, whether there is a special sentence between the signal of this structure is to that structure. And it's also possible to prove this without relying on the solution to Hilbert's problem. And this is what we will do. But today, I start by we could see how we can do this by just the perspective. And so, what is this structure that we will be interested in? So, the signal type. They consist of a constant symbol, which we name the L3. And then we have a binary function symbol, which takes two keys, A and B, and then combines them into three, where they delete the left subspace A, and they delete the right subspace B. And then we have this function symbol of arithmetic, which is supposed to be this substitution operator. And so, what is the universe of this structure? And it will consist of all finite full matrices. So, the universe consists of all very multiple times. Let's just the constant symbol and the binary function symbol. So we have this, which stands for the between, and then we have this, 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 and so on. So this will be the object, and then, as I said, this will remain the same, and then this function is some point. And opposite. And then, how do we calculate this? So, this is supposed to take 3 inputs. So you input 3 fields, T minus, and what you do is just you take T, and you look for all the corners of part in T, and you replace them with S. So each occurrence of part is replaced with S. And we can describe these corners. So if T becomes part, then we will calculate this. If T does not equal R, and T is the entity, we just calculate the entity, and T is not equal to R, and T is equal to 1, then we can get so, for example, let's say that for T, we get this here. Let's say for R, we get this here. And then we identify the occurrences R and T, and we have and then if we say that S is just the entity, then we could get that this is witness this part is identity case we can get this. Any questions so far? And so very good. What we want to look is that when just does not exist. So very complete. It's just the equation. Then we have to yes with this equation have a solution. And we have to here with the equation as a solution. there is no ability, but exogenity intelligent expressed in this signature and tells us the equation has a solution for that. And but there is one ability to object the equations have a solution. It's sufficient to show that there is no ability. Not checking the right line with the existing surface is to be organized. And perhaps you can see like this. The first observation is that the soft relation can be easily defined in this structure. So R is a subfield of T if R occurs in T. So for example, this is a subfield T because we have the occurrences of R. And how can we express the subfield relation in this structure? Let's just use this to denote the subfield relation. And we can define it as follows. S is a subfield T, it can only be S is a subfield T, it can only be take T and look for the precision S, and then replace this negative, and then what we should get is something which is equal to what is happening. And once we have this, we can use the following reductions. So if we have two equations, S1 equals P1 and S2 equals P2, we can combine them into one function using this parent function. And then we have to do something about inequalities. So if we S is not equal to T, then S is not a subfield T, or T is not a subfield S. So, and then we can use this here in this part here becomes that. We have T and we S T. And then this here becomes S. That is ridiculous. And so, if we start with an existential sentence, we can push out the existential quantifiers and get a quantifier matrix. And then we use these two transformations. We apply them on the matrix, and then what we do is just this function of equations. And then to check whether this is true, we just need to check whether these individual equations are the solution. And so, if we could decide whether equations have a solution or not, we will also be able to decide whether an arbitrary sentence is true or not. So, it's sufficient to check that there is no argument for deciding whether the existential sentences are the existential sentences are true or not. And
I think that's the algorithm. This method you allow you to categorize such a sentence or this disjunction to just exist before it is all.
yeah,
So this important thing that is taken.
absolutely.
It was also instead we just with regard to the simplicity of the fixed problem since because the junction is not conjunction, not and we know how to do both negation and conjunction.
Oh, but we always use this one. You always introduce this one.
Yeah.
So actually, I don't know if whenever you have an arbitrary existential sentence, you can compute formula of this one that is equivalent to it. In other words, I don't know whether we can there is a way of it. And another question which I don't know how to answer is in the case of the arithmetic, we know that every computer with any other set of natural numbers is existentially defined. But in this case, if you have a computer with any other set of finite invariant things, is it existentially definable? In this scenario. I don't know whether the answer should be yes or no. So, I will say this here. Yes, we can try to see how we can existentially interpret arithmetic in this method. And so what we will do is identify the local numbers with an existentially definable set of finite fundamental increase. And then on this end, we can express addition and multiplication using existing operators. And then once we have that, we can then conclude that there is an ability for deciding whether the line change is existing. And also we can start by trying to see how we can encode numbers as trees in a way that is simple enough that we can exist and define this set in the system. So one relatively simple way of doing this is to say that let us identify 0 with this tree here, and then let us identify 1 and this tree here, and then 2 will identify this here, and then 3 which identify this. And we can see the middle part. So you have that 10 plus 1 is 1, 2, 3. Where you have that's how you the 1. And this n is not to something which has n plus 2 difference. So 0 is not something with 2 difference, then we get 3, and then 4, and so on. And the collection of strings of this form will be existential. And before we start from that, let us see that we can have some minor variations on this. So let us put the sum today. Which is not there between. So, for example, in our case, in this question, alpha to be listed here. And then what we do is that we want to identify 0 with alpha, identify 1 with alpha, and this is identified with this. And we do general n plus 1 identify. Oh, let us just like this as 0 over alpha, 1 over alpha, 2 over alpha. And then we can say that n plus 1 over alpha is n over alpha, and then we just have this. And let's so let us consider this set, which consists of these representations of all natural numbers, starting with 1 and 2 and so on. And the first thing is that this thing is existentially defined. So perhaps we can see why. I'm going to erase this. one is that P. So then let's pick an arbitrary P, and we want to decide whether it belongs to this set or not. And we have that T belongs in the alpha, belongs to B. Here, we put the one alpha. So here is this three here, or representation of one, or remember that this is the subtree relation, then we have seen that it's something that we define. So, or two is a subtree of T, and you have this equation. And T is equal to either T is the representation of one, or T as this three is something, and it satisfies this here. So this so if we take T and we replace this with that, then we get the left side of T. So why is this the case? So we can start with the resimplification, which is that all is set on that property.
Shouldn't we be starting the set from 0 overall point? And having the same thing for between the other alpha and the 0 alpha? What is it?
I mean, it's just by choice that I think it takes 0. But
yeah, right, you don't need 0.
If I know that this is existentially definable, then let's say I get one or so.
Yeah, you can actually choice.
Yeah. So let us see an example. So let us see that. Say for the presentation of power. So this is this we have 1, 2, 3, 4, 5. And then this here is the subtree, which actually represents Q. And then if we take the 5 over alpha and we replace with 1, then I will actually be looking at this nodes here and removing 1. So I will get is 1 and so we have that so this is that this is good. And then the other implication that the only things with this property are exactly was this. So this inclusion will be running up chain on the sides of T. Okay. So let us assume T satisfies this equation here, or this formula here, that T is either so we have this one, which is that T is this, and that's okay. We have added this, and the other case is that we are in this situation. And so, let S then be this one here. Let S be so, since this right here is a subject of T, and we are replacing several things of this with S3, which is smaller. This S should be smaller than T. And then we want to use the induction hypothesis on S. S is smaller. And then I am going to raise down. And no. First, the one possibility is that image is equal to the representation of 2, and then this will be okay. The other case is that this here is a proper subject. And so let us recall that T looks like this. And we know that this is a proper subject of T. What does it mean? It means that occurrences of this tree can only be found in S. Because either for this to be a subject of T, it means that either it's equal to T, or it's a subject of the immediate right subject, or something of the immediate right subject. But it can't be a subject of this because it's too big. And we are not considering the case where T equals is here. So we are in the case where occurrences of this cannot be found in S. So, this here is a subject of S. And we already have then one of the conditions satisfied. And then we do a computation to see that this equation happens. So we have defined S, we do T, well, with the Q, and replace it with 1. And then we know that it looks like this. You have S, and then you have 23, and then and we know that occurrences of this in T can only be found in S. And so we get that this is S. We have it 2, replace it with 1. And this is unchanged. And we can, this is just another way of doing it. Yes. So we see that this is satisfied. And then by the induction of parentheses, we get that S belongs to this here. And then since P is equal to S, and we add this with one on this three, we must also have that. If S represents 17, then T represents 18. Yes. That will be the end of this. This kind of direction. And the questions simple.
I think kind of the real problem is how we do the visibility. Yeah. What happens in the again, of course, the kind of way of representing this way of representing numbers is easy to do like it because it's a problem.
Yeah, but
yes.
What's actually maybe this surprising, or maybe not, or maybe surprising, in fact, when I was looking at this, first I saw that this is true. And then in the multiplication, you actually use a similar idea. So we see. And then from that, you can also import computations like putting machine using a similar idea without relying on the custom power. By just working with this directly. And it will be like one level up from how we will deal with the pitch. So, is easy. So if we want to find 3.4 plus 2. So now on that one, 3, and 2. Right. And what we see is that we are just taking this here and replacing this alpha with time. So we can say that x plus y, that's plus y, and we put this x. So everything is quite easy. And then what's next is multiplication. But perhaps before we look at multiplication, we can explore multiplication and see that this way of representing numbers, we can also use a similar idea to represent finite strings or by finite alphabet, and this will also be existential. So let us, for example, look at how we can identify and find these strings. Well, what we can do is we can keep with them. First, we can pairwise interpretable with respect to the sum to the relation. And then this will be our empty string. So that will be empty string. And 0, and then, for example, the string is 0, 1, 0, 1. The present was the string 0, 0. Okay. I'm going to be A. And the set of one such trees will be existentially definable because we can look at the trees and the following form. We can look at this and then so we can look at trees of this form, which will just be another way of representing the natural numbers. And a similar idea to that shows that this set is existentially defined. And then how do we get from this in such trees? Where you just take an arbitrary tree, and then we take some arbitrary tree, and then we press with A, and then we should get something which is this one. And then if we get something in this form, then we know that it's coming from something like that. So we also get, and of course, concatenation is also very easy. It's just similar to how we did condition. You are just go into. です。 But here I'm replacing it with something else. We can here. So we want to see that multiplication is also a essential defined one. And so just to look up the idea. Let's take two non-zero natural, three non-zero natural numbers. And we want to express that n times k is equal to n. And what we do is that we talk about the computation sequence for this operation here. So we say that this equality points can only be there exists as different of x we have 1, 31, and 2, and 3, and 3, and 2, and 1, we are subpoints. And 1 is 10, and 1 is 1, and then we have that 10 the other one is 1 is plus 10, and that's 1 is 1, and then we have that 10 is n, and okay. So we want to say that n times k equals n, we can only replace this such a sequence what satisfies this question. And so what we want to do is that we know how to represent natural numbers. And now we want tree that encodes this sequence. And from that tree, it should be easy to treat these numbers here. And then we should also have this way to identify this tree. And what we do is we start by having two different representations of natural numbers. So we have one representation for the sequence of n's, and one representation for the sequence of n's. So what we do is that we keep three trees which are pairwise incompatible with respect to the substitution. And then we represent, let's say, the sequence of k's using alpha. And we represent the sequence of k's as using beta instead of alpha. And then, so let's see how, for example, we can currently that records that I am living because 50. So what we do is that we start with discover, and then we go up, and here we have our representation of 1 using alpha, and here we have our representation of 5 using beta, and then we go up more, and we get 3 represented using alpha, and here we have 10 represented using beta, and here we have 3 represented using alpha, we keep doing represented using beta. And from this tree, we just need to look at the right subtree, and then look at this subtree again, which is 50 and 3. And then we are seeing that we go from here to here by adding 1. But we go from here to here by adding 5. Similarly, we go from here to here by adding 5. And so, given an action number 10, therefore the molecular one, let us consider the set of trees of different ones. So what we do, we include the tree which we call that when comes 1 equals 10. And then we have another tree which we can start 10 times 2 is 11. So then we do one of the trees. And we just continue this one. So for each one of the number n, we consider the set of these trees. So elements of n code of multiplication of the family. So then you put 10 times k or something. So now 10 times 1, 10 times 2, 10 times 3, 10 times 4, and so on. And then the claim is that this set is existentially definable. But not just that, the n here can be just actually as a prime one, which is coming from, let's say, this circuit. So we have the formula that xn as a parameter, or n representation of n, and then this set will be existentially definable. And then once we know that, we can get multiplication, because to check that n times k equals n, we just need to go to n of n, and then we search for a tree of this one, which is such that when we look at the immediate right side tree, and we go down to the left, we find k, and then once we know one, we know that when we go to the right here, we have the definite complete. So the final task is to see that these sets are the essential defined. So then we go to this node. Let's see. Right. See, is take along with it the following concern. In fact, one we have that of this is a factor of p, and this is certainly the case for how we have expressed this. We always have this thing at the shell, and then the other thing is to do something similar to what we did in the previous case. It's that there exists and this here and on such that the following equation. Well, so first we want to get a minus b. And what's this here? So I will not this here. Transport and for this operation, suppose I do this substitution. And when I'm done, this substitution. And after that, this substitution. So we go into T and we replace this with gamma. And we replace this with alpha. So first we do this substitution. And then we get some of it. And then we do this substitution. We get some of it. And finally we do this substitution. And this will be the immediate left substitute. And then the right, the immediate right substitute will consist of two pairs. Where one pair is coming from this set here, and the other one is not this set here. So the proof will just be as what we did in the original test. One implication would be easy, so we can use this here as an example. So for the suggestion, let us take this reality, and our end now is 5. And then, so we have this here belongs to alpha. This here belongs to here, and then if we take T0 and we reinforce the select this replace this thing here. With gamma. What we get this, we are taking this, and you know the and that's the test gamma. So we have gamma, and then we have alpha, and we have the and delta, and then and because we have chosen alpha, beta, and gamma will be pairwise equal with respect to the substitution, we can find this field, for example, inside this pattern. So when we do this substitution, we are just removing this part and replacing it with one. Then let us take and we do the second substitution, this one here. So let's see one, 0, and we replace one of and what we get is the following. So remember that elements of M alpha look like this. Elements of M beta they look like this. And one of that alpha just looks like this. And so when we go into this here, and we want to replace occurrences of this with the alpha, what we are doing is that we are going to this and subtracting one from it from them. But we are keeping this fixed because we cannot find this here as something of this here. Or this here. And then finally, let us take T1 and do the final substitution. What we get is this. Then is 5. What we are going to this once and remove the 5 from each of them. So when we have completed these three substitutions, we actually have this. So we see that elements of this set of this map. And then we want to show that the only thing is those properties are elements of. And I'm going to erase one, the space. And then I'm going to machine. We do the other integration by action on the size of so assume it satisfies one input. Then there exists two of the numbers. And such that is here. It is here. Is so then first the this in here we have that T is equal to this. And here we have the dimension F, and then we have another top. So we are, and everything is equal. We see that they are not same. So, first we have that S is generality. So we want to use the reduction of the basis of this. And we want to show that S satisfies this result. So we have the two cases. Case one is that S is equal to gamma. Right? So we have that T is equal to gamma and but we also know that this thing is a subset of T, which we know looks like this. So, what are the possibilities? The possibility is that we have that this thing is the same as this thing here. The other possibility is that this thing there is a subset of this, but that's not possible because this is independent. The other possibility is that this thing here is a subset of this, but that's excluded by how we chose gamma to not be comparable with alpha or delta. So the only possibility we are left with is that we have that T is equal to this. And then we know that T belongs to
It should be down on the top, right? Just the final.
Where it should be that. Okay. So this is one case. The other case is that the S does not equal gamma. And if S is not equal to gamma, then T is not equal to this. And then, yeah, we have T is not equal to and what does this mean? It means that occurrences of this three in T are only found in S because they can be found here. So what we have is that is what that is a few tests. So we have one now. Then the next is to do a computation to see what we have an equation like this. And so let's do it. And then how that S is defined like this. And we know that T looks like this. So we have here. This. So we want to this thing and force to do this substitution, and then this substitution, and finally this substitution. And we have already seen that occurrences of this in T, which is this thing here, can only be found in S. So when we perform this substitution, we get that this will be S. And here, we should just have this fixed. And then we need this substitutions. And then the next is to perform this substitution here. And where can occurrences of this be found? Well, they can be found here. First of all, we cannot count that this is equal to the whole tree because we have gamma inside here. So this can either be found inside here, or it can be found inside here, but not here, because we find delta are in the. So what we will get is that when we do this substitution, we get this. And what does this mean? It just means that this is A equals 1. If A is greater than 1, it's very balanced. Because what in here, since we are thinking then of the here, we could just have alpha here, and then when we do the substitution, nothing will change. And then finally, we do this final substitution. And what we do is that occurrence of this can only be found here and here, but not here. So we are just going to do a substitution inside here. And inside here, then keep this part there. It's so. And then we get that. Yes, it is. Again, here we have that when we do this operation, we have the usual subtraction. If n is greater than n, why we keep n? It's because it can be imagine that this here is just some number smaller than n. And then when we do the substitution, nothing will happen because there is no appearance of the n basically. But now what we see, we have a that this is exactly this. So one is okay. And then we have two that t looks like this. Now, S looks like this. And we see that this holds because this here belongs to what? And this here belongs to Madison. And the immediate left subgroup satisfies this equation. So, by the hypothesis, S belongs to N. And then when we know that S belongs to N, then we get from the fact that T looks like this, that we place here, and this and this here. When we go down to S, we are removing the 1 in here. And on this part, we are removing an N. And because we know that S belongs to N, this here, we write that E1 is equals to and so on. And this here has to be a multiple thing. And so we get that is also an and this shows that these sets here are existent at the final. And you see that and here it's also putting as a function that is coming out from here. But we can go from here to here very easily using the substitution. And once we know that the ends are existent definable, we can get the definition. And I guess this is what we want to say. Yep, great. 3 minutes of time.
That's delayed. So
what's the quickest way from here to get recursive functions?
So, as I mentioned,
Like the procedure is, yes, you can do something similar and just have like an extension statement or there is an element where 0 occurs in a set. But this cannot be used whatever.
can we repeat what was
Like I was thinking, or you can like index a set by having it be like a pair of elements. The first being the index, and the second being like some
I guess, the value of your recursive function, and then like if you can state when it is the first time where zero occurs, because well, you can like I just rewrite the same thing as it being like a subtree, well, as an extension statement with it being like the tree of this element, and when you substitute like the zero with something else, then you can do it also manually without substituting it.
So basically, doing some extensions.
Yeah, I'm doing this in my coding stuff.
So,
I don't know if there is some easier way to model it.
so for example, the word I implement what we have said is to look at also on the view that looks like this, but and we also want to have an easy way of going from here to here, going from here to here. And what I use is that I use the post correspondence problem, because you can go from Turing machines to post correspondence problem. And post correspondence problem is about one else. So you have a bunch of formulas, and then you want to list them with the repetition amount, so that what you get, if you need the string on the top and you need the string on the bottom, you will get the matching identical strings. And using such formulas, we can include the exponentiation, so that, let's say, if we always start with this formula in our listing, we get a matching if and only if here we have the an output which coincides with so let's say that here something like this, so then we have a bunch of formulas, and then we get a matching if and only if we have the correct input and correct output. And the nice thing about that is that we get a simple way of going from here to here, because we are only, so we can post the margin just the string on the top. So we say we list the first element, that's a string again, and then when you add the second element, we get bigger string, the third element, we get bigger string, and we can let these strings be what's applicable. And then to go from here to here, we are enlarging this string by attaching one of these. And similarly, go from here to here, we are enlarging it with one of these. So we have a finite number of choice of going from here to here. And so what we do is that we have a tree which encodes the sequence we get by using the first part. And then we have another tree which encodes what we get when we use the lower parts. And then the other tree is to say that those things are identical, but we also need to know that when I
Because that we're reading the same number of slides.
when not just
Oh, yeah, right.
when I use this here, I have to use the people. So I have to also make sure that the rules match. So the strings match and the rules are matching. And the way to do it is actually by having a fancy function or something like this. So if you want to look at the difference, you can see it. Upside. Was that the satisfactory answer?
Yes.
But what I have not been able to know is whether any computable function on the edge or just any subset of edge, whether it can exist at the time. Because we know that it's just some subset, which is the representation of natural numbers, we get all of them. Or even if it's some subset of strings, we can also do it. But what if we can arbitrarily set, compute a set of this physically set? I don't know what the answer should be. In the case of natural numbers, we know that that is free. That is it in this process.